Um, so now we get back to hemoglobin and a couple other respiratory pigments. Now, as I go, I'm going to have to remind myself what's in red and green ink here, but um, here is this idea. Oxygen doesn't dissolve well enough in water, in the water of your blood, for that to deliver enough oxygen to your cells. So what has evolved are these molecules, mostly hemoglobin, that can grab oxygen much greater than plain water grabs it, carry it around, drop it off. So here's that. Before we get to that, again, I'm anticipating someday reading those IB syllabus for what they want you to know about different animals. But I doubt this shows up. But here's one of them. Here's another respiratory pigment. Instead of iron, it has copper as the metal part of it, so to speak. So their blood is kind of bluish, which is what copper is, a little more bluish. And so this you find in things like cockroaches and many mollusks, has evolved to be its respiratory pigment to help carry oxygen around, right? Tell me all you know about hemoglobin. I will stop in class to pick your brain about that in a review kind of way. So here is an aspect which, when I flip the next slide, I might see if it's in red or green ink. This is called cooperativity. If you remember, one of the things you wanted to tell me before was that hemoglobin is organized at the quaternary level. It's a single protein molecule that has more than one polypeptide chain as part of it, in this case 4. And here's what cooperativity means. When an oxygen molecule actually gets grabbed by one of those subunits, of which hemoglobin has 4, it changes the shape of it enough to change the shape of these so that they can grab oxygen more easily. Cooperativity. It's like the 4 are cooperating. And when oxygen leaves this, then these 4 also change their shape and give up oxygen more easily. So both for the grabbing of oxygen and for the letting go, oxygens show cooperativity, or excuse me, hemoglobin show cooperativity among their 4 subunits. We can see that in this dissociation curve. This is what I thought. This is in green ink, right? They would want you to know this if we were doing the optional unit. So maybe someday I'll teach this again, but I'm going to do it real fast here because maybe they would show you this graph as part of a story and ask you, can you read graphs and things like that. So what is the dependent variable here? What percent of hemoglobin is saturated with oxygen? That means it's carrying all 4 because that's as many as one hemoglobin molecule can hold. What percent of your hemoglobins are saturated, right? Well, a very high percent of your hemoglobins are saturated if the concentration of oxygen, which for no great reason is referred to in this term called partial pressure. I never understood the need for that. It's really just concentration of oxygen. If the concentration of oxygen in your blood is really high, again, it's not 100%, but really high, like it is in your lungs, then hemoglobins are really saturated. That should make sense, right? But if the concentration of oxygen in the blood in your tissues, like at rest, is quite a bit lower, that means oxygen saturation is quite a bit lower. When you're exercising and your tissues have less oxygen because they're using it up so fast, the hemoglobin is a lot less saturated. So what does this show? This shows when there's little oxygen around and then its concentration starts to increase just a little bit, your hemoglobin gets really better at grabbing it. This really positive slope here is indication of cooperativity. When your tissues can start to grab oxygens, when they don't have much oxygens grabbing on hemoglobin, your hemoglobins rather, and they start to grab them, they get really better at grabbing them. And then if you add more and more oxygen, they just can't hold as much more. They've already gotten pretty good at grabbing them, so their grabbing oxygen curve is not quite so steep. If that made sense, fine. If it didn't, don't worry about it, because this is Corona year and you don't have to answer this on the test. So this is something we talked about before. And if we go back and look at the IB things from past, we might see this. I don't know. But this was a good adaptation. If, again, now you're a little Joey, a little fetal Joey, right? So your head is not in the dog's butt, right? But you are physically connected to mom across that thing called placenta, and mom's capillaries are getting real close. Actually, mom's blood is getting real close to your capillaries and that organ we call the placenta. What's going to cause your blood to grab oxygen from mom's blood? Why should mom give up oxygen to you? Well, mom's not making a choice here. It's that in that time of your life when you are this, right, when you don't have a name yet, you use a different gene for making hemoglobin. This is where we first saw this when we talked about gene families. And this is also gene regulation. At that time in your life, you're using that gene to make this kind of hemoglobin. It's got a higher affinity for oxygen. All grown up mom has stopped using the gene that makes this and uses the gene that makes this, adult hemoglobin. And your fetal hemoglobin is better at grabbing oxygen from her adult hemoglobin, and that's why it goes across the placenta into your blood. So that's a good thing for you. Really neat system that has evolved that way. I'm gonna skip the Bohr shift. I'll say it real fast. What that little shift means, this should make sense now. If the pH is low, what does that mean? Carbon dioxide concentration is high, a little more acidic, right? But what does that also mean? That means oxygen levels low. High carbon dioxide and low oxygen go hand in hand. At a lower pH, your hemoglobin is less saturated than at a higher pH. That's a good thing. That means your hemoglobin gave up its oxygen more easily, because it's when it gives up its oxygen that it gets less saturated. So that little difference, figured out by physicist Niels Bohr, hence the name Bohr shift, right? That little difference has to do with a very functional adaptation in terms of, boy, if oxygen really gets low, it's like your hemoglobins have evolved to squeeze a little bit more oxygen out of themselves so that you can get it into your cells. So this is still in green. This shows you that, focusing on carbon dioxide now, how is it carried around in your blood? Well, some of it is grabbed by hemoglobins, by their amine groups, not by the iron part, but by their amine groups. A decent percentage of it. About only 7% is actually dissolved in the water of your blood. But then some of it, a good bit of it, in fact, some of it, most of it, like it says in big letters there, is transported as part of an ion, which is also that kind of ion we call bicarbonate ion, which is basically like baking soda. And so in your blood, carbon dioxide gets chemically transformed into this hydrogen carbonate stuff, which if you had to take this on a test, you would have to learn that you don't want to call this bicarbonate, a more common name, because they chose to call it hydrogen carbonate. So there's that chemistry, right? Carbon dioxide reacts with water to become carbonic acid. That's the acid part we talked about. And then that chemically reacts to become this bicarbonate ion. And this is now what most of the carbon dioxide locked in a bicarbonate ion travels around in your bloodstream and into your tissues as bicarbonate ions. So then what happens when those bicarbonate ions get to your lungs, which have a low carbon dioxide concentration compared to these tissues, which are coming back from your working muscle cells and stuff like that. Well, now that set of chemistry goes the other way. This becomes that carbonic acid, which gives up its carbon dioxide, splits into water and carbon dioxide. The carbon dioxide now in high concentration diffuses towards where it's lower. That stuff you should always recognize. So if they told you this whole story and asked you questions about concentration gradients and stuff like that, questions about pH and stuff like that, you should be able to answer those parts, but they're not going to ask you to identify these parts. So this is neat. We might do this in class because we can kind of simulate this. This is an adaptation. This is not part of the syllabus at all, but so I'm going to kind of skip through it here. We'll talk about it in class. Here in the green part, which you don't need, they throw one more. We had hemocyanin, we had hemoglobin, and now we have myoglobin. Myo is the muscle word. So as its name suggests, this is a globular protein that's found a lot in muscle cells, right? And it is a really good oxygen grabber. And so in kinds of animals that have both hemoglobin and this, you can think of this as kind of like a spare tank of oxygen. The oxygen in these kind of seals normally gets grabbed by hemoglobin, let go by hemoglobin, but some of it also gets grabbed by myoglobin. And if they need some extra oxygen, like when they're on a deep dive, which is what those last few slides were about, then that oxygen is going to come from this spare tank called myoglobin. And so this is neat, called the dive reflex. We might get some people to dunk their heads in ice water here in a minute in class and have fun with that. So, so here's the last one. I'll do this in class because this is a great review of lots of different things. What is the difference when you're in good shape and not good shape? You're still the same person, right? But you clearly have different characteristics. You don't get so tired. You can do this, you can do that, you can do that. What is physically different about you? I'll give you one good example. When you're in good shape, every one of your muscle cells has more mitochondria than when you're in not so good shape. And that's one reason why you have more endurance, because you can recharge your ATP batteries better because of more mitochondria. I'll ask you in class to try to fill in more blanks. Okay? I mean, this shows one of them right here. There we go. That's it for that one.